Hi everyone, welcome back to ICTS String Seminar Series. So for this week, we have Nabamita Banerjee from IISER Bhopal, and she'll be talking about near horizon dynamics of near-extremal black holes in higher curvature gravity. Over to you, Nabamita.
Thank you, Athira. It's really very nice for me to be here. Actually, this is my first time here in ICTS. And I found this place like very much similar to HRI, where I have done my PhD, very calm and quiet, far away from city and two shops outside, which exactly like how HRI used to be when I was a student there. So it's really nice. And thank you for having me here. So today I'll be talking on this work, near horizon dynamics of near extremal black holes in higher curvature gravity. This talk would be based on a work that I have done with my student Mukta at IISER Bhopal and postdoc Tania there and Arnab, who was here last week. And then I'll tell you about some of the calculations that we are trying. We are trying to understand some part of it now. So based on both of this, the talk would be. Please feel free to stop me any point whenever you want. Okay, so let me begin. No. Yes, thank you. Okay, so the plan of the talk is following. So I'll be first telling you about some recent developments in the field of near-extremal black holes and understanding their dynamics. Then I'll talk about the near-extremal black holes that we will be working with. I'll talk about their semi-classical thermodynamics in the context from two derivative theory perspective. And then I'll talk about, I'll go to higher derivative theory and say how these things changes. Then eventually I'll go to the effective two-dimensional description of this system. And I'll talk about two distinct regions that play a very important role in understanding the dynamics of these black holes. Next, I'll come to the computation of partition function, where I'll tell you that how one can understand these systems in terms and then eventually I'll go to the Schwarzian description of which is at the boundary, which will be sitting at the boundary of the space-time. I'll tell you exactly in what sense it would be so for two derivative gravity, and then I'll explain how this whole picture can actually be contributed to nice higher derivative. And then finally talk about the thermodynamics and give me then important discussions on the whole study. And then I'll conclude and finish with some results. This one is a I just want to go to the next page. So there are two chat messages. Yeah, I'm not speaking actually. Just that's fine. Okay, so let me start. So we know that understanding the properties of black holes has always been a very interesting topic in physics, and so far
We can't hear you.
Yeah. Okay. So I'm just going to stand here. Okay. Right. So recently it has been understood that Jacob-Teitelbaum beam gravity, or shortly that we call is jetty gravity, which is a two-dimensional theory of gravity coupled to dilaton. And this reduces basically just to a boundary theory when one works with it. And it is claimed that this theory captures the near horizon dynamics of higher dimensional near-extremal black holes in two derivative theory. So this is a work, I mean, this was first talked about in this paper by Maldacena, and then Trivedi et al. And Turiachi et al. Have made much progress into this. And they have shown that so far the near-extremal black holes that appear in two derivative gravities are considered. Their near horizon dynamics can actually be understood in terms of a jetty gravity theory. In particular, it will just eventually boil down to a boundary Schwarzian theory that I'll show you in minutes. Okay, so but the point is following, that if one does a semi-classical analysis for this system, it implies that there should exist a mass gap between the extremal and the near extremal black hole. I'll also show you it in few minutes when I'll give you the semi-classical thermodynamics data to you. But using the jetty partition function, then it has been shown that there is no such mass gap even for non-supersymmetric theories, and rather the semi-classical description is just not good enough when one goes to very low temperature. One needs to consider the quantum effect into account, and when one does that, then it can be shown that there is no such mass gap and things are nice. So this 2D pictures actually offers a very simple way to compute logarithmic corrections to near extremal entropy, and here I mean logarithmic corrections which are dependent on temperature to near extremal entropy. So this is the work that has actually been done in this paper by Turiachi. It's a 2008 paper, 2020 paper. Okay. So the question that we have asked is following, that we know that higher derivative terms actually play an important role in the study of black hole entropy. In particular, for a certain class of extremal black holes, actually one need to turn on this higher derivative curvature terms to get a non-zero entropy, non-zero extremal entropy for these systems, and that very nicely matches with the microscopic description of these black holes. So we can expect, and it's natural to expect, that those terms will also be important in the context of near extremal black holes. So what we'll study? We study the near horizon dynamics of near extremal black holes in 4 derivative theory from the 2 dimensions perspective. And we will show that it is effectively again described by a jetty-like theory with a particular only R square higher derivative modifications. It would be clear to you that why only R square when I'll go ahead in the talk. And the R square corrected jetty theory is again described by a Schwarzian-like boundary action. And using this partition function, one can compute the partition function even in this case, and we can find the temperature dependent logarithmic corrections to the entropy. So this is what I'll show you in the talk, and then I'll make some comments and more discussions on it. So please feel free to stop me at any point. So let's study. So yes. Sorry. Yeah, I mean that the mass gap will not be there. I'll explain that. Okay. So to begin, I'll first explain you that just from the semi-classical analysis why one would expect the mass gap, and then I'll show that how when one takes the quantum effects into account. That. Okay. So let's begin. Okay. So for most of the talk, actually, we can just concentrate on the 2 derivative gravity. I'll show you how the results modifies in presence of higher derivative gravity and what are the subtleties. But the basic physics are same in both cases. So let's go ahead. So the near extremal black holes in the context of 2 derivative gravity. So all I'm doing is I'm considering Einstein-Hilbert theory, And I'm also considering in presence of a cosmological constant term, which is not important. We can do this analysis as well for asymptotically flat black holes. Again, the basic physics doesn't change. Okay, and since we want to impose a Dirichlet-like boundary condition on the metric, and I also want to fix the charges. So one needs the appropriate boundary terms to be added to the bulk action for the well-definedness of variation problem. And what the boundary term that is required is following. This is well known and nothing new. Okay, so one gets basically a solution to this system as a 4-dimensional ADS Reisner-Nordstrom black hole. And the near horizon geometry of this is, one can find that this is a spherically symmetric electrically charged solution. In particular, in the extremal limit, it has ADS2 cross S2 in the near horizon geometry, where the values of the radius of ADS2 and S2 are following. So the S2 radius is what I'm calling as phi naught square, which is same as the radius of the extremal horizon, related to charge via a relation like this. And the ADS2 radius is like this. So you can, from these expressions also, you can check that one can nicely take the one can flatten off the space-time completely, and the relations become simpler actually. So this phi naught is the extremal radius, and the mass m naught and the extremal entropy s naught are basically phi naughts of functions of this charge q and phi naught. So I'm going to study this system in terms of these two parameters. Either I'll probably call it phi naught or RH, and in terms of q. These are my parameters. Any questions so far? Okay. So now this was the extremal geometry, right? But our interest is in studying the near extremal solutions. So how do I go near extremal? So our way of going to the near extremal solution would be following, that we are first of all we want to understand this system for a very small temperature. So my T naught would be small, and the way I am going near extremal is following. We are saying that we are just keeping our charge fixed, but increasing the value of the mass above its extremality by a small amount. What it effectively does is, it takes me away from my extremal horizon. And now I have to, because it's no more an extremal solution, I'll have two horizons given by this relation. If you remember, the extremal horizon was called phi naught. So it's now I have two distinct horizons, phi naught plus delta and phi naught minus delta, where delta is a parameter which is just directly proportional to the temperature of the system.
Sorry, now, what is L capital? What is L capital? L.
Oh, L capital is this, the radius of the the cosmological constant. Okay?
Okay.
Okay. So now, if one just finds that thermodynamic quantities for this system, one finds that the energy is this, or the mass gets corrected via this relation, the entropy gets corrected via this relation, where this m gap, the parameter that is appearing here, is related to the extremal horizon, and these are the two parameters. So here, this is where the statement of mass gap becomes important. See, from here we see that the change in entropy above extremality is proportional to T square by m gap, right? So if we are working in a temperature where T times m gap is very less than, first let us think about less than 1, then we'll talk about equal to 1 also. If it is less than 1, then the change in energy above extremality would be a very small parameter. Right? And hence, like, it would not be possible. I mean, if the particle wants to go to the, if the Hawking radiation, if we want to have Hawking radiation, it should have at least the required energy, and here we don't have it. So the solution to this problem was that, well, it's not possible. One cannot go to a T which is less than this whatever cutoff value that I'm calling m gap. So there should be a cutoff. There should be a mass gap, in other words, and I can lower my T as low as that. Now, in the context of supersymmetric black holes, such a mass gap is expected. Supersymmetry gives such a mass gap. But here we are not talking about supersymmetric black hole. In this entire seminar, we are not going to talk about supersymmetry at all. So when I don't have supersymmetry, there is no reason to have such a cutoff. Okay? So then why should there be a mass gap? We would expect that a black hole can have as small temperature as we want, a Reisner-Nordstrom black hole, and we should be able to see Hawking radiation from it. So that was the confusion of that was the, I wouldn't say confusion, that was the issue with mass gap. And but if we just want to stop here, the semi-classical analysis definitely says that it is not possible. One should have a small energy gap, and that should be the energy gap between an extremal and a near-extremal black hole.
Hello, can you hear me? Hello.
Yes.
Yes, I have a question that why do you call that it's a statistical breakdown of the statistical description? That I didn't understand.
No, I mean, all I'm trying to say that, like, if I all I'm trying to say that we won't be able to describe Hawking radiation from this picture. I mean, it doesn't go together. That's what I mean.
So yeah. I thought that statistical description, you mean the microstates of the black holes.
No, I'm not. No, I'm not there. No.
Okay. So that is about the Hawking radiation.
Yes.
Okay.
Yes, these are. Whatever comes with this T naught, yeah. This is M gap is a fixed quantity, right? It just depends on my parameter, and that's what it comes. Right. Right.
Now, what is so special about when T naught becomes larger than M gap?
So yes. So what I'm trying to say is, look at this. Not from this formula. Look at this formula. So the E minus M is the energy above extremality. Okay, so if T naught times T naught by M gap is much less than 1, then what we are seeing here is the energy above extremality is less than T naught. So that, but then how would, so it doesn't have the required mass to radiate. That's the issue. But if T naught is, okay, now what would happen if this is just equal? If it is just equal, say one quanta will go out, but after that the problem will come. But if it is greater than then that problem is not there. So I'll come, Subrat. So the solution that people thought is that my T naught can never go below this. I mean, my T naught will not go below M gap, and hence I should have a mass gap in my theory. Yes, Subrat.
I might have said it another way. This parameter M gap is 1 over N, the way you defined it, because L2 is the cosmos. L2 is the same as capital L previously, or
L2 is the effect. L2 is the effective radius of my ADS2. I mean, the radius of ADS2.
I see. So it's basically some parameter which is like 1 over N, right? It's what controls quantum corrections, this M gap. So presumably you're saying if the temperature, if you go to the next slide, please.
Sure.
Presumably your point is if the temperature becomes smaller than 1 over N, then you don't have a good semi-classical description of Hawking radiation because it's the same parameter that's controlling quantum correction.
Yes, you can think of it like that also. Okay. And hence, like, yeah. But if we do not look at this equation and just think physically, why can't I not have a Reisner-Nordstrom black hole with as small temperature as I want?
You can have, right?
We can have, right? So that says that we cannot stop. I mean, this expression, if we just think that this is the expression, then we are making mistake. This expression should be, we need to look back at this expression. This is just semi-classical design. So as you were saying, that we probably, when my temperature is going below that, I probably cannot ignore the quantum corrections. And that's exactly what these people said. Okay, fine, good. So this is what we will try to understand in this talk, that how to compute the path integral for such a geometry. All we are doing is we are just fixing boundary conditions that at the asymptotic boundary of ADS4, and then for the above range of temperature. So we are interested in temperatures which will belong to such a range, and we want to see that if in this temperature we can really compute the path integral, then how these results are going to be modified. I need extremality. So all I'm doing is, I mean, the way I'm looking at near extremal is I'm demanding it to be just away from extremal. So just to answer you for Schwarzian black hole also, if you are just considering a non-extremal black hole, the corrections, well, these are not temperature dependent corrections, but the Euclidean path integral has been computed. But we will see that it's very different when it's small temperature. Okay,
I have a naive question. I mean, ordinary entropy is associated with the temperature, right? I mean, even say.
Oh, I can have temperature. We can have entropy even for 0 temperature black holes. Those are extremal black holes.
I see. Okay.
Okay. So now let me just in one slide tell you that what kind of a theory we will actually be interested in. So for us, our theory will be definitely the one that I showed you earlier, the 2 derivative gravity. But with it, I'm going to add arbitrary high derivative corrections after 4 derivative gravity. And although in this slide, I have only shown you the higher derivatives, 4 derivative terms involving metric, but the result that we are going to get would be applicable for all fields. For all fields up to 4 derivative, the result will be valid. Okay. And of course, one needs to take the appropriate boundary term properly to do calculations. Here, this lambda is a small perturbation parameter. So I'm going to treat my higher derivative terms perturbatively in this analysis. And this RGB is the Gauss-Bonnet combinations. It's because we know that in 4 dimensions, this is topological. So basically, my result will non-trivially only depend on these 2 parameters and not this. Okay. Yes. Yes, yes, yes.
So your answer will not depend on.
My answer will not depend on this. Yes. And I'll show you that. Yeah, answer is yes to you. I'll tell you later. Okay. So first, let us look at the extremal background for a black hole solution in this theory. So it is again a spherically symmetric. We can have a spherically symmetric extremal black hole solution, and it will have a SO2,1 cross SO3 near horizon symmetry, which is basically just telling me that we'll always have a ADS2 cross S2 in the near horizon of the extremal geometry, and the scalars will take some corrections. So I'll tell you how the things are being corrected. One can just do sense entropy function formulation appropriately for this system, and one will get this. Nothing very difficult. So that's all this slide is telling, that when we are interested in a extremal black hole in this theory, the near horizon geometry is going to be corrected appropriately. One can find the entropy, extremal entropy, as well as one can find, whenever we'll go to near extremal limit, we can find the temperatures also for this system. Okay, now comes the main part. So as I said, all we wanted to do is we wanted to understand how to compute the Euclidean path integral for such systems. Yes, that's all. Okay, good. Yes, I'm treating the higher derivatives part of it. I'm keeping only the linear terms in lambda. Yes. So the idea of Maldacena, I mean, primarily from Maldacena, and then very nicely done by Sandeep and his group at IIFR and by Turiachi, is to show that there is an effective 2-dimensional description of this system. So how one gets to that? Let us first understand this. Okay, so we are interested first of all in background that has spherical symmetry. Okay, so we have our theory and we want to understand properties or path integrals for all those backgrounds, for fluctuations around all those backgrounds which has spherical symmetry. Please stop me at any point if you want to. Okay, so in such a background, what it does for us is we can reduce the theory from 4 dimension to 2 dimension by expanding our fields in the spherical harmonics of the S2, which are like YLMs. Okay, we know this. And the field answers, which are consistent with this Kaluza-Klein reductions over S2, will now have, in the massless sector, we will have 2-dimensional metric, a dilaton, which is going to come from the radius of the S2 part, and then some gauge fields, the U1 gauge fields in the L equal to 0 sector, and SO3 gauge fields in the L equal to 1 sector. This is what is going to be the massless sector of my theory. Okay, And the effective required part of the reduced action is going to be following. So I'll definitely have a term like this. This is going to come from just square root GR that I had in 4D. I'll have a non-trivial dilaton dependent potential, a F square term whose coefficient will now again depend on dilaton, and then other boundary terms, and SH are terms that will, I mean, these are like kinetic terms for the SO3 gauge fields. I have not written it because I'm going to, in the rest of the talk, I'm going to concentrate on just L equal to 0. The work can actually be extended to L equal to 1, but that's just technicality. So I'm not going to present it here. No approximation. At this level, all I have done is I've just reduced my theory over S2. No approximation. Yes. And just to tell you that this is a phi dependent potential, which is pretty non-trivial. Okay. Next. Nothing. I haven't done anything. All I have done is I have just done a Kaluza-Klein reduction, and I'm giving you the massless. Yes.
So right now you're not considering higher derivative gravity. You're just considering.
No. Right now, this expression I have not given you the higher derivative. How would this expression modify in presence of higher derivative? I'll tell you how it will. I mean, it's just a long expression, so I'm not giving you. Okay.
Yes.
Good. Okay. SA should be the kinetic term. Kinetic term and other term involving the SO3 gauge fields. So basically, say suppose I'm interested in a non-rotating black hole, then I do not need to consider it. But this whole analysis, even if I keep these terms, will actually go through. Okay. Why it would go through is because of the next statement.
Sorry, Nabamita, can I ask a question?
Yes.
So do you also expand the metric in spherical harmonics? Or what do you expand in spherical harmonics?
Everything. So all my fields, so I'm just doing a Kaluza-Klein reduction, right? So I have to, so the vectors, the tensors, everything I have to expand appropriately.
So the tensors should have some tensor spherical harmonics which have some angle dependent pieces, right?
Yes. It
Where
will.
do I, so
that is why I will get. That is why I'll get. Okay, just give me a minute. Maybe See,
yeah, sure.
This is what is my. Did I answer you? This is the case. Will do that job.
I see. Thanks. Okay.
Yeah. Okay. Yeah, I was here. So now, since we are in 2 dimension, so of course the gauge field strengths should always be proportional to the Levi-Civita tensor, and that makes life simple. So due to this simplicity, the gauge fields can actually be integrated out. I mean, one can do it consistently and it's not difficult. So once one does that, and if we are just concentrating on the L equal to 0 sector, then what we are going to have is a resulting action, which is an effective action involving the 2D metric and dilaton only. Okay, so at the 2 derivative level, the action is going to look like this. So I have an action involving the dilaton field phi, the metric G of the 2-dimensional space, some non-trivial potential of the dilaton, and the boundary term that we are going to have here. And this M2 is my 2-dimensional space. Okay, so if somebody was asking, so if we keep the higher derivative terms, then this expression is going to be modified. I'll definitely have this part, but other than that, we will also get various 4 derivative interaction terms involving again the metric and derivatives of phi. But we can integrate out the gauge fields completely. That's the good point of it. Any questions so far?
If you integrate out the gauge fields, don't you expect a...
so this U phi will take care of it. Okay, so this U phi is very non-trivial. I have not told you what it is. It is a non-trivial function of phi. But it does not involve any derivative of phi.
No, but the gauge field is mixed in the metric also, right? I mean, I suppose.
Right, I'll show you what it is.
Yeah, in the expression for the metric, this, yeah.
Right. So one has to, so you have to do it appropriately, like this F has to be expanded in terms of the Levi-Civita. You have to use the properties of that. And then using that, you can integrate it out. I mean, this requires a bit of computation, which is not difficult at all. And what you will get finally is following. Okay.
Why don't you get higher derivative terms in the R?
I will get. I have just not written it.
Okay.
Okay, as I'm saying, at higher derivative orders, we will get various higher, particularly 4 derivative interaction terms involving R and derivatives of phi. It's there in the paper. It's a long expression, so I have not written it. Okay. One has to consistently do it and one will get it. Okay. So the point that I wanted to emphasize up to this is that by doing this without any approximation, what we have is an effective two-dimensional description for my system. Okay, so if I take this and if I can somehow find the Euclidean path integral for this, for fluctuations around, for this action, then we are getting to the results that we want to get. Okay, good. So before I do that, I want to tell you that it would be good to look at the geometry a bit closely. So the effective 2D descriptions, one can just check that it has a classical solution with the metric being. Huh? Huh? Okay. Here they are not there, but I think in the paper of Turiachi they have considered that. Yes, they have considered it. Yes.
So you're essentially ignoring the higher derivative terms when you consider the effective 2D description?
No, no. So what I will, so right now I'm just trying to explain the physics of the system in the context of two derivative gravity, and then I'll tell you how it extends to higher derivative gravity. I'm not ignoring them at all. For the time being, I have just kept them aside. Okay. Okay, good. So what I want to say that this effective two derivative description will have a classical solution where the metric would be ADS2 and the dilaton would be constant. One can show that that's a solution of the equation of motion. And that actually corresponds to the extremal geometry in 2 dimensions. Okay. So now what we do is we can actually look at the near extremal geometry in 2 distinct regions. So what I mean by this is following. So we have an extremal geometry, that's fine. It would be the extremal geometry would be ADS2 for metric and dilaton phi would be some constant. Let me call that phi. And now we want to just understand how the near extremal geometry. Okay. And the way I want to understand the near extremal geometry is following. I want to understand the near extremal geometry in one region that I'm calling the near horizon region of the near extremal geometry. So this is near horizon region of the near extremal geometry, and then a far region, which is just the extremal geometry, full extremal geometry. Okay. No, this will correspond to the acha. What is your question for extremal geometry? Yes, yes. Is.
It starts from infinite, followed by infinity, and then it goes down to.
So the dilaton is actually just the size of S2, right? Isn't that constant for the extremal geometry? Yes. In the near, not in the full geometry. I agree with you. Right. This statement is not for the full geometry. Yeah. Right. So the full geometry is the full extremal geometry. Whatever it is, but I know. I mean, we know the full non-extremal geometry. So finding the full extremal geometry is simple. So that I know. But then I want to understand how this geometry should be looking when I'm zooming to the near horizon. Okay, let's say these are my 2 regions. We have to know what it is, and I'll tell you at the end of the talk what it is. But next, what I'm going to do, of course, so this is a region which would be the near horizon region, and then I have this region that I'm calling to be far region. And what I'm supposed to compute is, I'm supposed to compute a Euclidean path integral over the whole. Right? So the way we would do it is, we will split it into 2 parts. We'll do what? Okay, I'll show you. And of course, again, here, before I go to the next slide, I should say that there should be a boundary where the 2 are different, and all we should demand is at the boundary, everything is smooth. So if we can make sure of that, so there is a boundary, and the boundary that separates these 2 regions, let us call that RB. Yeah. And all I want is that my field should be smooth at this boundary. If that we can do, then one can do the calculation in one region involving this metric, in the other, I mean, involving this geometry, in the other region involving this geometry, suitably taken care of the contributions coming from this boundary, and effectively we'll have the full result. Okay, so that is what we would be doing. I'll show you. Okay. So that's what is going to be our strategy. So we want to compute the Euclidean path integral of this effective two-dimensional theory in the near-extremal background with appropriate boundary conditions. By this boundary condition, I mean the boundary condition at the asymptotes of my space-time. And the strategy for this computation is going to be following, that I'll compute this action, which is now a two-dimensional action. I'm going to split it into these two parts, whereby the S2D NHR, I mean that I'm going to do the R integral. I'm basically just splitting the R integral from RH, from the horizon, from the extremal horizon to this RB, and then from RB to my infinity. Okay, and accordingly one has to take the boundary contributions, which should be coming from the boundary that I have placed at R. So if one can do that, then one will be able to hopefully go ahead and find the partition function. So very good question. You were saying that to begin with, there is no RB. RB is something that I am putting by hand. So in the end, it should not depend on RB. Yes, your statement is correct, but the fact that there is a boundary is important. Where the boundary is not important. But yeah, it's little subtle, but I'll tell you how. But the fact that there is a boundary, the fact that there is a boundary that separates these two regions is important. No, I mean, so my entire result really does not depend on where RB is, but it depends on the fact that there is a boundary. Okay? Yeah, it is fixed actually. L2 is fixed for you. Okay.
And why shouldn't you take the integral from 0 to RB?
Oh, because like, I mean, my space-time is defined from RH. That's my horizon. Okay. Okay. And then the way we should be approaching this problem is following, that in these two regions, in the two distinct regions, we are going to turn on fluctuations around the background. So the background will depend on in which region we are. And similarly, we will also turn on fluctuations in the scalar field in the dilaton phi. We have to impose appropriate boundary conditions at the boundary RB. That is what I have given. Basically, we are just saying that the boundary length is fixed and the fields and the metric and the dilaton has appropriate, appropriate fallout. And with these two inputs, what one can show is that this above action will take this form. Okay, but this expression, as you can see, let us look at this expression. The first term is just simply beta times m naught, which is going to come from the background. The second term that I have written here involves the fields to linear order. Particularly here, if you can see, this one depends on phi. Phi is my phi naught and g mu nu background are known quantities for us. Phi and delta g mu nu are the fluctuations. So here this action is just linear in phi. It does not depend on delta g mu nu at all. In fact, it does not depend on this term is also 0 because, okay, just a minute. This term is also 0 in the near horizon region, because in the near horizon, my background is just ADS2. But then I also have terms which should be higher order in fields. So this is where we have made the approximation. I mean, this is an approximate statement. That my 2D action would look like this is true up to linear order in fluctuations, and in higher order fluctuations, I'll have more terms.
So at some point you put the extrinsic curvature because there was a boundary. Where did
Right.
the Gibbons-Hawking term come from?
I have to take that.
You put it by hand. No.
No, what is
Where
it?
did the Gibbons? Yeah. This
Why have I imposed? Okay, so
where did the Gibbons-Hawking term come from?
sorry. Yes. This one. Yes. So here the Gibbon-Hawking I need because I have my full space-time has asymptotic infinity.
Equals infinity, but
This is at R equals infinity.
move it in, right?
Now, exactly. Now what I'm doing is, so see, one term is just this, right? So here, if I take this action, or not only I'm taking this part of the action, I'm also imposing this condition. Now, as soon as I'm imposing a Dirichlet boundary conditions, I will require the appropriate boundary term. Otherwise, my variations won't be well defined.
But the question was, I thought the philosophy was we'll start from an action in 4 dimensions
Yes,
and we'll reduce it.
right.
Then the action is what it is. We can't now say I'll add
No,
a term to the action.
yes, but the fact is, when you are doing that, I of course know that like this background is not one background, right? So that is what I showed here, that my full action would be combination of both these two. So for example, this part, now I have to start from RH plus delta B to infinity. So here at RH plus delta B, which is RB, is also another boundary for me.
Are you saying you're adding and subtracting a given?
Yes. So no. So from the near region, I have no boundary term. Because that is what, see, I told you what my SF2D is. This is my SF2D. To
Originally
begin
you
with, I just have this boundary term.
Originally it was at infinity, but I thought in the final action it had come to the near region, right?
No. So what I'm saying is, when you take these two and then follow this prescription, follow this prescription, what you get is an effective boundary term here, which very nicely looks like exactly how it should be for jetic gravity.
And that's what I'm asking. How did it come?
How does it come? So it comes from these contributions. Yes. So here I have to integrate from RB to infinity, right? And here this is what it is. But now I am also imposing this condition that at RB from both sides metric has to satisfy appropriate boundary conditions. So I mean, in particular, Dirichlet boundary conditions. So when I'm doing that, then I need the boundary terms. So this will give me that.
So sorry, need the boundary term is different from saying that it will come from the original Einstein-Hilbert action. You're saying you just take the original Einstein-Hilbert action,
Right.
and you break up the integral into 2 parts. One
Right.
below something, one above something, and
Right.
maybe I guess also an integral over the boundary contributions. And you're saying that somehow can affect.
It will give me this. Yeah. So when I'm going to this expression, I can show you the details also. When I am finally coming to this expression, this and this together and this, all these three together, of course, this has nothing to do with the boundary that we are talking about. This and this together will give me this term. So it is important that physically it is important that I have to consider the far region. It's not, if I do not take the far region contribution in account, then I do not get this boundary term. And this boundary term finally is the most important one in this analysis. Absolutely. Yes. Yes. I'll show you the calculation. Okay.
Suppose I just take the Einstein-Hilbert action and take about the full space. Right? And now I want to break it up into 2 parts.
Yes.
Right? I don't know anything. I don't want to do any calculation. I just want to break it up into 2 parts and try to make sure that the variational principle is well defined.
Yes.
Right? Then I have thought just to make variational principle well defined, I have to add a boundary term there. Right? From the point of view of the near region.
Right.
But also from the point
of view of the far region. Yes.
I have to add a negative boundary term.
Right.
And they will cancel.
No.
Right?
No. Because like the normal that I would need for the near region and far region will not be proportional. The geometries are different.
No,
so I need to find a normal.
It's a smooth, no? It matches smoothly.
At the horizon, it matches smoothly, but
the boundary, yeah.
Yes, but at the boundary, the two normals, the normal that is coming from the near region and the normal that will come from the far region will survive. They will not cancel each other and will give you this.
Saying you're adding and subtracting k, is that the adding and subtracting k and you keep one k on one side and the other k on the other side?
Yeah, that's what I have thought.
That would have been natural. That's what I also thought. But Nabamita, you're saying that's not what is happening.
No, that's not what is happening. So, yeah, I mean, I can show you the calculation later on. Okay. So what it does is, you are right, but in that process, the way I have to write this term, I require the two normals and they are not parallel. So those two combinations will not cancel. Some part of it will cancel and this will survive. No. No. Well, in fact, first of all, their directions are not same.
They're opposite.
But not only that, they're opposite, they're not parallel also. In fact, if you compute the two ends, they don't come out to be parallel. It's one surface, yes. No, but they are not, they are not same. So what they are exactly and how this this term, just a minute, I'll take your question. How this term exactly comes, I'll show you. Okay, but for the timing, let us go ahead and let me say that this term is there. I'll show you at the end of
it. You're not adding anything extra?
No, I am not adding anything extra.
By manipulating the original action?
Just by manipulating these two, I'm getting this. And what is important, I just want to mention is to get this term, I do need contributions from the far part as well. So it's not that I can forget about the rest of the geometry and can only do calculations in the near horizon region, then I don't get the boundary.
Okay, so I can also put it this way that you add and subtract this term.
Okay.
Okay. And then you have added this term, you keep it as it is.
Right.
What you have subtracted, you put it inside the far one.
Far one.
Then manipulate the far one to show that there is
that is yes. You can take it like that. Yes.
Okay.
Everything else would become zero, only this will survive. No, but the part that I am subtracting or adding in whatever sense, that has, this part is there, right? Particularly this part is there. So this part is doing something, and either you think that it is giving me that boundary term, or you think that whatever extra you added, that it is killing that part.
Yeah. So I think what I understood is that you add and subtract, right? You keep the one that you have added in the near region. Whatever you have subtracted, that together with this action plus the given shocking term at infinity somehow cancels and gives you zero.
Yes.
Right? I think that is how.
Yes.
Yeah, that it doesn't contribute at all.
It will not contribute to this order. Yeah.
If I understand, that's what you are saying.
Yes, that's what I'm saying. Yes. That is how I will show you how it works. Yes. Okay.
I have a question.
Yes.
Like to start with, when you when you take the Einstein-Hilbert action, it's defined over the entire space, right? To start. Now, I don't know what the Gibbons-Hawking calculation is really, but do they kind of do this? Do they ignore the interior of the black hole and consider the?
No, Gibbons-Hawking term is a term that you need to add with your action for the variation.
Not the Gibbons-Hawking term, but the Gibbons-Hawking analysis. In the Gibbons-Hawking paper, do they consider only the exterior of the black hole, or do they consider the entire space-time?
Sorry, Somdata, maybe you can ask this later.
Okay.
Okay. Okay, but another important point that I want to make here is this whole, from this step, so please remember that I had a non-trivial U5 sitting here. From this step to this step, it is only correct up to terms which are quadratic in my fluctuations. Okay, and here, as I was saying, although I have written this term explicitly, r plus 2 by L square, but it's actually not there because r is equal to minus 2 by L square. So all that I am getting, the non-trivial thing that I am getting here is this term, of course, which is the leading term. Again, it's a constant term, and this term, which is a boundary term. I don't expect a linear term. Exactly. All I am doing is just I'm considering fluctuations around my background. So linear term should not be there, and it is not there. That's not at all a non-trivial statement, but yes. So, but on the other hand, Ashokda, my theory is SF2D, right? So I am truncated. I have not truncated it, but what I'm saying is this is the form up to linear order, and then I have higher order terms here. Okay, good. So this linear action is the Jacob-Teitelbaum gravity action with the appropriate boundary term, but in the NMR region only. So now we can say that if we want to understand the system up to linear order in fluctuations, then we can forget about the far region. We can only do the we can only do the computation in the near horizon region, but added this boundary term. Okay, so this is the full thing, and this full thing together is what people call is JT. But I mean, to me, all we are really getting here is just this boundary term, because this is not there. So I don't know if it is right to call it JT or not, because gravity is not dynamical here. Okay. Sorry. No, but JT is a theory where gravity is dynamical, right? No, it is not. In fact, I mean, I have written this term, but I should not actually. Because my R is minus 2 by L square, no? See, here R is, I'm supposed to compute it over the background. In the near horizon region, the background is extremal background. No. This. Yeah.
R is the background.
Subrat, this. I'm doing this.
If you include the phi square and delta T square, then you are delta T.
R and what? Yes, so, but then it is not JT, Subrat. That's what I'm trying to say. The way people find, the way people show that it is JT is basically just looking at linear order action. And that is what I find very surprising, because it is not, I mean, it is just a boundary term. Yes.
You can compare it.
Yes, but then that term is, but what is JT? JT gravity is this, right? Where? Yeah, JT gravity is phi or phi square, doesn't matter. R minus 2 by L square, or what I've written, my notation class. And then the boundary term, the appropriate boundary term, square root H phi. Okay. Yeah.
And expand up to quadratic order.
Yes. The first, you mean?
What you wrote on the board.
Okay.
That you could expand to quadratic order, phi and delta. Right?
That I can do in phi and delta G. Yes. Yes.
And you could compare with the order phi square delta T square.
Okay. Yes, that I can do. But okay. I don't think they look same. No. Okay, good point. So you were saying that but what am I doing? So first of all, see, look. This is what you get, right? This is what I get from after dimensionally reducing my thing. This is no way JT, because I have a non-trivial phi potential sitting. Okay, JT is this. Okay, so now, yes, you can say that let us just do this and not do this. Okay, if I do that, then by that you mean that I am setting the metric to my background value anyway. But how would what do you mean by that? I mean, my full classical solution is phi equal to phi naught and G equal to G mu. Yes. You don't expand it, it's fine, but you are computing it on what? Right now we are only at G2, so every statement is in G2 only. I mean, in 2D only. So, Subrat, that I have already done, right? After doing that, I am here, right? After doing that only, I have a term where there is a coupling between R and phi square. This is full R. Here there is, this is the action. This is the 2DR. Yes. U of phi is a non-trivial phi dependent potential. Okay, which is like, which involves no derivative of phi, but higher powers of phi. What one does it, one expands it around the background. Right. And yes, so when one does that, one sees that to linear order, it looks like JT. But then the point is to linear order, actually I'm not supposed to get anything because this term is 0.
And you just expand in 5, not in G. Not in metric, but 5.
See, you can choose not to introduce a delta G. That I am fine with. No, how? But the metric is still some. I mean, you are fluctuating around your classical solution, right? Your classical solution is whatever is your background, which is ADS2 in this case, and a constant electron in the near horizon region, in this region. Now, around that, I see this is not a field redefinition, I must say. Because if I do field redefinition, then I cannot just stop at phi order. I have to keep other terms. Now, if you keep other terms, then only you get this. I mean, that is what you should be doing. But then that is not JT anyway. Yes. I'm not understanding how would I do that. Because, sorry. First order around what? No, but I thought like, okay, sorry. I'm saying so much because I myself want to understand this. So my understanding is this is my action and I can expand it around a background. The background is phi naught and G is ADS2. You can choose not to expand around it, but you have to set it to some value, no? That is okay. To begin at this step, both the fields are dynamical. I agree with that.
You have to check that it makes sense to keep up the linear order in phi and arbitrary order in delta. You can keep arbitrary high order in delta.
No. But I will show you that that will not be the near horizon geometry, by the way.
Linear order, there is no delta G anywhere.
Yeah. In quadratic order, I'll have delta G. So in the quadratic order, I will have non-trivial dependence on delta G. One can find the solutions. And that is not, yeah, that will not be ADS2. That's what I'm trying to say. This is R of delta G, which one? This one. This term. I agree with you completely. And that is why, I mean, so far the literature only talks up to this. Yeah. I thought finally the Schwarzian property is what is important, and that will be here. And what you were saying, I have to check because I'm not sure that one get, but I'll check this. Absolutely. In fact, for the rest of the calculation, that is what is going to be important. But a very good point. I'll check that again. I was somehow thinking like this, that I am expanding it, right? So yes, I can decide only to expand the dilaton, but I'm expanding it around the classical solution. So then up to this is what you have, and then this term is actually not there. I have written it, it's like falsely. I mean, it doesn't have any value. And yes, I have non-trivial terms here. That's correct. But I am not sure that I mean, I have to check that, but that combines again into a form like this. In fact, to my knowledge, if it looks something like this, it goes as phi square and then r, I don't remember, some term L square, and I can be wrong with the factors, but two terms here and then other terms. I have it somewhere, but I don't remember it exactly. Right, there are other terms also. I'm just writing one term. So there are other. So one term comes like this, then there are other terms also. Yeah, I mean, I think I should have metric fluctuation, because if I don't turn on metric fluctuation, I don't, even the phi becomes trivial. Because this k is also for ADS2, na? Yeah, this k is also for background. But up to this, no. There is, I mean, this is k for ADS2, that I can say, but now I have to integrate it over the boundary. The boundary being seen non-triviality, right? Because yes, at the boundary, and that is what will give me the Schwarzian. Yes. No, it's not for ADS. In locally it is ADS2, but I also have the non-trivial boundary. Yes, yeah, that's correct. That is what this term would do. That's what gives the Schwarzian. No, bulk does nothing. I mean, even for JT theory, even when for this theory one computes the partition function, all this bulk does is, I will first integrate over phi. All this term does, it tells us locally everything is ADS2. Because I'll get a delta function, delta of r plus 2 by L, which will tell that r has to be minus 2 by L. Even there, the non-triviality comes from here only. Okay. Let me go ahead. Yes. Yes. The consequence. Exactly, I agree. The consequence is, most important thing is this. This survives, nicely comes from the far region contribution, and it gives me the Schwarzian. I agree to that.
I mean, you have two fields. You have delta G as well as phi. So which is going to give you the Schwarzian and the phi of the Schwarzian?
This part will give me the Schwarzian. It will give me a Schwarzian action, which will come from the modes of the of my metric, which is living on the boundary, which are non-trivial.
But the phi is related to the radius, as you said before, right?
Phi naught is the vacuum. I mean, the vacuum expectation value. On that, I am fluctuating phi. So phi is like my field now. But at the boundary, you see, I have set phi. I mean, this is the boundary condition. So at the boundary, my phi is some constant value by the appropriate cutoff. So in this computation, this phi will actually just go out as phi b by epsilon. Epsilon is cut off. And then this k will bring in the non-triviality. One has to regulate it properly, adding a counter term. And then what one gets is a Schwarzian action. Probably I'll have it like after.
Initially, didn't you say that the phi naught was related to the radius?
This phi naught?
Yes.
Yes, but now we are looking at phi, right? Small phi is fluctuations around phi.
That's what I'm saying. So the Schwarzian phi is related to the fluctuations of the
Schwarzian, no, the Schwarzian, no. Schwarzian is not of phi.
Phi in the Schwarzian is usually related to the fluctuations of the radius, right?
No, Schwarzian is not going to be of that of phi. It only depends on phi. It cannot be Schwarzian, right? Schwarzian involves derivatives. So the Schwarzian, I mean, just wait, I'll show you the Schwarzian. Yes, sure. Yes. Yes. Right. No, very good point. So I will get it. I have to keep this term. Yes. Because yes. So if I don't keep this term, then like there is no meaning of it. Like phi is just constant, right? Yeah, so I have to, so to get what this phi is, in fact, to know the form of the dilaton, I need to keep this term, I need to find the solution, and one gets the solution. And there I also get the solution for delta G. Now I don't remember it, but one gets. I have to check that, okay? I mean, what I'm trying to say is, what I'm trying to tell you is that so far people in the literature just look up to this, I mean, this piece and say that it's JT, which does not look right to me. One needs to keep this and see that up. Finally, in terms of this delta G, I am getting the JT. I am not sure that that has, I mean, at least the literature is not clean on that. But I agree with you that that's important. Okay. Good. So now, so all we understand here is that then for my actual calculation now, with this boundary term, I can just concentrate in the near horizon region, do the fluctuations and do my work. By that, I basically just mean that I am fluctuating the metric. The delta G that I wrote earlier is now I am just in this gauge, I am taking it into the factor, into the scalar factor, and the phi I am expanding with these background values that I had. Sorry, I have written tildes here. I mean, somehow I have gone to the higher derivative term, higher derivative effective theory, where these guys are just replaced by the phi naught and L2 is replaced by their tilde values. Other than that, they're same. Okay. And as we just saw that when one does that, then what one gets is effectively a linear order action because the other term vanishes on the background and it just gives me this boundary term. This is exactly same as what we saw here. Okay. Now the other two parts are because I have higher derivatives. So it's yeah, one just has to take the boundary terms properly, do the calculation properly, but you are right.
JT gravity or in, let's say, not derivative gravity, we have seen that in first order formulas, we can write down it in some kind of Poisson sigma model. Can you do that in high derivative?
That I do not know. But what I will show you, see, right now, all I'm doing here is from the perspective of the fourth derivative theory and reducing it. So I'll show you later on that how I can modify my JT, appropriately modify, add the proper terms in the in the JT theory boundaries, the Gibbons-Hawkins boundary terms, such that I reproduce this. So that was basically the arbitrary. So for us, it's arbitrary. Yeah. One can compute it perturbatively. At least for up to fourth derivative, yes. So that is, so when I'll just show you. Kya ho gaya? Sorry, have I done something? Okay, let it be. Huh. Tell how to get that, right? Yes. So for, I'll show you. No, I have to put the boundary term. Right now the boundary terms are at infinity. Yes, yes. Same required form there. Yes. Yes, so this is that boundary term. And for a higher derivative, I mean R square and RAB square, Gauss-Bonnet is trivial. That perturbatively can be found. So this is the boundary term, only 2 order lambda. Yeah, I forgot. This is, I think, a paper by Sarah. I should have added the reference. It is not in my hand. At the, so you mean here in this region, in the, so yes, so the one I have at infinity, I mean, what do you mean by that? No, I need them. Yeah. Right. Right. For yeah, I think even for R to the power 8 also, and Gauss-Bonnet, but also, I mean, for Gauss-Bonnet and also probably for R to the power 8. But this, yeah, here I needed it for generic 4 derivative gravity. For that, it can be found perturbative. Now, okay, I can go, but is that? So that is, so the fact that I'm finally, so that is what this this thing is, right? So I am finally getting, I'll show you, just so I'm just finally going to get this. That's the nice thing, yeah. Yes. 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 As a perturbation. Right. Right. Because, yeah. So, right. Yeah. So it is perturbatively in that sense, yes.
Here, this combination is, like field definition invariant. I mean.
So I checked that. Okay. So what I'll just show you later let me see where it is. Just. So what I'll show you is that I'll start with a theory in 2D. I probably that's not a direct answer to your question. And here you can actually have other higher derivative terms also in 2D, involving the other fields. But then you can do field redefinition and can first minimize to the set that you need. And then using the fact that you are in 2 dimension, you will only be left with R square. So, and this with the boundary term actually reproduces the result that I showed you. So the field redefinition part is taken care in this, which would definitely have a meaning in the other picture also.
Then what happened is that because we also have Maxwell term, then try to change the arguments to that, but we get an Maxwell. So the Maxwell term are not normalized. It probably cannot allow it. Yeah, I don't know. But at least some extra ones will be physically don't allow the Maxwell term.
Only has one. Yeah. Yes.
These two parameters that allow you to change, right, are G mu nu goes to some multiple of G mu nu and R mu nu, right? Okay. Or R times G mu nu and R mu nu. These will correct the Maxwell term in 2 different ways, right?
Yeah.
Because they are not the same, they are different tensor structures. One will be R mu nu coupled to the stress tensor. Other one will be R times G mu nu coupled to the stress tensor. Somehow, right? And I think, or maybe the, maybe that then that combination you can get rid of. Yeah. I think it should be checked. I mean, what happens in the Maxwell term? Yeah.
Okay. So this is what I was saying.
You're integrating out the Maxwell field by integrating out loops of gauge fields, right? From the action, or how are you doing it? It's a quantum correction, right? So you're integrating out loops of.
Maybe you can actually.
I can answer this question later on. Is that okay? Yeah. So there is a paper I think from Witten that nicely describes how to do it. Okay. So here, where was I? Sorry. No, where was I? Yeah. So this is at the linear order. This is what it looks like, and yeah. So all the non-trivialities in just in this the boundary integral, and from the second order piece of the action, one can find the fields, these two fields, the fluctuation fields that I have taken, phi and omega, and in particular, phi admits a solution of this kind. So whenever this phi is 0, if I set the constant such that the phi is 0, then we are at extremality. And the running of phi slightly changes the geometry, the near horizon geometry from ADS2 to something else. So one gets a omega also. So that is how things changes here. Okay. Okay. So yeah. So yes. Question. So now I just want to say that how this two derivative JT action actually gives us the Schwarzian term, but probably most of you know it. So as I said, like the only non-triviality is here in this boundary, and what it does is it breaks the symmetries, the JT, the full JT, it breaks the symmetries of ADS2. So at the boundary we have non-trivial modes. When one takes that into account and then uses phi equation of motion, one can finally show that for those boundary modes, what one gets is an action like this. Okay, so here these TUs are boundary modes. Again, the Schwarzian that we get is for the boundary mode, but please notice that this whole term, I have written the partition function directly. So here the term is only non-trivial when I have this phi b. And what was phi b? Phi b is the boundary value of my dilaton. So if I set my dilaton to 0, then I have nothing. Okay, then we get no contributions. But when we set that to the bound, I mean, on a constant value at the boundary, we can choose this. This is a parameter for us. We can choose it accordingly. Then one gets this non-trivial contribution to the partition function. And right, yes, yes. So I'm saying at extremality, this is 0. So this term is not there at all for extremal cases. This is purely above extremality. Yes. This only phi b will be replaced by phi tilde. Yeah. So yeah, and one can actually show that this is one. I mean, this is an exact result. So the result is actually one loop exact. So this is the full contribution, full quantum contribution that one will get. Okay. Okay, so this is what I would just say for higher curvature gravity, how the things are modified. So motivated by this two derivative analysis, we just want to see that if this boundary action can actually be obtained from a JT-like theory now with suitable for derivative modifications to the action. And the modification that we propose is following. So we are proposing some term, which is, so here V, R, and Z are constants that one needs to fix, and we will fix it appropriately so that we get the right boundary term that I just showed you earlier. And as I was saying that here only one term, only one higher derivative term after field redefinition is possible, and keeping in mind that we are in 2D, it is possible, and that's just R square. Okay, and the full action here looks like this. I have removed the constant here, nothing else is removed. So this is the full action with the appropriate Gibbons-Hawking term with corrections added. And when one does that, basically one has to do the calculation. I mean, one can basically see what would be the contribution. If this is how my JT is modified, then how the partition function or the Schwarzian is going to be modified. Again, perturbatively in lambda, one can do that, solve the system appropriately and set the boundary conditions again appropriately, choose constants that are appearing. For example, here phi b needs to be associated to this particular combination, and then one gets this. Okay, so at the end of the day, the result is that one gets back the similar kind of a Schwarzian. Only difference is this phi b now gets replaced to phi tilde b, where phi tilde b gets contributions to corrections to both in L2 and phi naught. That's it. And this is basically the result. And now once we have this, yes. This is the bulk. I mean, this is the full thing. So if I take this, so I find this. Sorry. Because the variation of this full thing would be finally well defined. I mean, it would be 0. I find what should be the term here so that the variation is well defined, perturbatively to order lambda. The Gibbons-Hawking term is still only the extrinsic, okay, extrinsic curvature with the coefficient having the data. So you can, yeah, you can also show that this is what you will boil down to if I start from the 4D and then do dimensional reduction also. Many things, yes. See, yes, but here we need to keep in mind one thing. We are in 2D, right? So all R's are actually only related to R. I mean, or RAB, RABCDs are related to R. So all K's will also be eventually just related to K. No, because I just wanted to, okay. No, I cannot get, I won't get K square. So let me show you. What did I have? Because I also need to make sure that the term is linear in phi. So that will also play a role. Where am I? Yes. So you see, this was my Gibbon-Hawking, right? This was also just always linear in K. Yeah. I'm sorry. G has 3 is the Einstein tensor, yes. And J is some combination of K. I didn't get it. Yes. Yeah. F square I have already removed. No, lower dimension I have no F. Huh. So what I can say you is that I get it and that works. Yeah. Which one? Not this. Yeah, I'll show you. Huh. Yes. And 2, yeah, since this term is already 2 order lambda, their R square is just 4 by L to the power 4. Yeah, yeah. That's basically what it is. I'll find it. I'll show you. Just, yeah, some constant. I mean, this I am taking that I get the action that I just got. Yeah. These are just choice, right? Or another thing that I said for this phi, I think this should be phi tilde. I'm sorry. So this phi tilde is this. Okay. So phi tilde B is nothing but this guy, but now both of them are corrected, and hence this is also correct. So this is what one finally gets. I mean, the whole nice thing is one again gets back the Schwarzian, and hence the computation, partition function computation is possible. The partition function just becomes this. And here T is the full corrected temperature, then one has to compute and take properly. And then the corrections finally comes like this. So here now I get back to the final, I mean, this is the basic, this is basically their result. The result of Turiachi et al. Is exactly this, just replace tildes by the 2 derivative data. That's it. So here you see, Subrat, that now my delta M, which is the mass above extremality, has a piece proportional to T. And that's what tells me that now I don't really need a mass gap. Right? No matter what small temperature it is, Hawking radiation is always possible. And yeah, that is, and this whole picture just, I mean, basically little non-trivially, but nicely works out in presence of 4 derivative gravity. So that is what we have shown. Okay, but this brings us to a very interesting discussion, and that is what I want to tell you. So you see the change in entropy here, if you see, it has a log term. Right? It goes as log phi tilde B times T. Just comes from, I mean, this is my delta F. So from delta F. If I just use the formula and compute it, I get it. So, but what that tells me is that if I just scale my parameters in arbitrary way by introducing small parameters, we see that this quantity, the change in the entropy goes like this. Okay, and hence, when these parameters are very small, this is a very large negative number. Now, of course, that doesn't make sense, but it is fine. We had I had a discussion with Ashok in IISER, and thank you for telling me this. So one can actually compute the density of states for this system, and one can see that the density of states just looks like this, where m0 is the extremal mass and E is the full energy, and E minus m0 is what is delta E, and you can see from here that the delta m, I'm sorry, that that goes with T. So when my T is very, very small, then actually the density of the density of state smoothly vanishes. So for such a system where the density of state smoothly goes to 0, we should not be looking at entropy. This is not a quantity, physically well-defined quantity to look at, but the system doesn't have any problem. The system is well-defined for as lower value of T as one wants to get to, and there is no mass gap. So that's what is the conclusion. Another way to think about it is what Polchinski and Almeri said, that they noticed it in the context of 1 + 1 dimensional gravity. There are also some issues like this were true, and they said from there that probably there is a cutoff to the temperature. Well, for supersymmetric theories, that's true. One does get a cutoff to temperature, but for non-supersymmetric theory, that's not true. And all we see from here is that probably we should not be looking at this quantity, delta S, that I defined in the usual way to define entropy, but one can look at the density of states and things are fine. Okay, so that's it. And let me conclude. So what we see is that the near horizon dynamics of a near-extremal black hole in 4 derivative corrected theories is captured by a Jetty-like theory with particular 4 derivative corrections, which effectively boils down to a boundary theory. Now, in higher dimensions, there could be more 4 derivative correction, in fact involving gauge fields. But when we are going to 2D, there is only one that is possible, and which is R square. And all one needs to do, basically the theory that in 2D that we have written down should, with different values of parameters, take care of all 4 derivative corrections added to your theory. That's the only thing. So in sense, we have understood what the correction would be and what the boundary term, what the Gibbon-Hawking term would be. After that, all that matters is choice of parameters. Then it's done. Okay, the computation leads to the vanishing density of states at sufficiently low temperature. Sorry, this part is not correct. And the perturbative higher derivative corrections actually does not change this particular physical feature. It still keeps the density of states vanishing. Yes. Yeah, that is not. That is not correct. I'm sorry. Okay. So what next? So as I was saying that at least from literature, like I showed you that the linear term in the 2-dimensional effective action is what people call that it is Jetty. The people don't really look at the next order term and take its effect into account for doing the rest of the calculation. So what we thought that would be good is to check somehow that this effective 2-dimensional description is really the description of 4-dimensional near-extremal black holes. Now, what do I mean by that? If I want to do that, then what I would really like to do is this question, that can we compute the near-extremal entropy from a 4-dimensional one-loop partition function? I don't want to go to this effective description. I just want to do a Euclidean partition function calculation in 4D for this near-extremal geometry, and can one get the same result? Okay. Now, this question can be addressed as follows. I mean, I am thinking in this way we can ask this question. Again, the idea would be to look for a near horizon geometry and then check its near horizon region and far region. So this part is fine, but now not in terms of an effective 2D description, rather in terms of the 4D description. And then to understand the effect of the boundary that is separating the two. I'll show you in the next slide that why the boundary is important even from this side. and then probably study the quadratic fluctuations around that and compute the one loop effect. At least perturbatively, this looks possible. This basically involves like perturbation theory calculation. So in principle, that looks possible. Okay, and then if one is successful in that, then maybe one can try to find a one can try to look for the microscopic understanding for this near extremal entropy. So just to show you something, so as I said, like what I would really to start with to understand these two regions. The far region is simple. It is again that full extremal geometry, the 4-dimensional extremal geometry. But the near horizon region is very interesting. One question. What one can see is that the near horizon metric and the near horizon gauge field now gets corrected like this, where this GAB and FAB is the usual extremal answers. This is just ADS2 cross S2. This is the usual Q by proportional to charge in the appropriate form, proportional to epsilon mu nu. And the corrections are following. Okay, so the ADS part, so mu nu is running over ADS2 and IJ is running over S2. So the ADS part gets corrected by this combination, and the sphere part also gets corrected by this combination. And most importantly, the corrected geometry is not ADS2. So in this case, the near horizon geometry really changes from ADS2. So if I just look at JT, it seems that the equation of motion tells me for metric, it's R equal to minus 2 by L square. That's not correct. That's not the geometry that satisfies the equation of motions in the near horizon region. This one does. Okay. So the geometry does not have ADS2 isometry. And since it does not have, so when one does computations around this geometry, things gets little more interesting. In particular, I just want to show you how the on-shell action looks like. So this. Right. Okay. Yeah. So I would get a omega. Right. So I had this delta G mu nu. Yeah. I'll get so when one takes that into okay, I have not done that. I don't know if that really boils down to this or not, but it should. And yes. Ashok's question is if I have solved for the capital omega also, capital omega, which was fluctuation in the metric. Huh. No. For JT, I have nothing new, Ashokda. For JT, I have nothing new. Yeah. Yeah. For JT, I have nothing new, but that. Yes. Yeah. But what I was saying is the 2-dimensional action was to linear order in fluctuation looks like JT, but there is a phi square order also. In fact, that is what, yeah. Yeah, I get about this, exactly. I agree. It should match to this. Yeah, I'm checking that, yes. No, it's not higher derivative. Right. But the rationale behind that argument is you can really boil down to JT, where it is just, where the theory looks like JT and they're just turning on phi. I mean, the boundary term is important and they're whatever, that's what is giving me. I'm saying that whole logic seems somehow not so correct. I nearly, yes. Yeah, this is in linear order in T. So I mean, so what I'm saying is following. See, you remember what I did is, I had a 2-dimensional effective action, right? This 2-dimensional effective action to begin with was not JT because I had a non-trivial potential for dilaton. What I did is I expanded it, and I took the metric to be the background metric, and then I turned on some fluctuation. Similarly, phi also, phi naught plus some small phi. The dilaton also like this. Now, when I'm writing this action, I see that the linear order in fluctuation, I get that square root h phi k term. And then I have terms in the action which are phi square and delta g square. I have this. I should be getting this, yes. Yes.
The saddle point with imaginary field.
Oh, this is the F, correction to F. F gets correction like this, yes.
It's a complex.
Yeah, that is correct.
Is it?
Yeah.
Okay, okay. Oh, right,
Field.
right, electric field.
This is just, then things would be different. Yes, yes. Which two terms? Yes. Phi B. That's the boundary value. Yeah, yeah. Set in terms of temperature. Yes, yes.
Are you saying that even if I take the temperature low enough, phi square term is competing with the phi term?
See, okay. So suppose I'm doing this, okay, and I'm just stopping here. I'm saying I don't want to look at it. Suppose. I basically have nothing from this equation, right? Because even like this phi here, this is a boundary term. This is phi B. Yes. Yes. Right. I would say that at linear order, the term that you are saying, I don't really have r minus 2 by L square at all. I mean, from this picture, if I'm coming from the, if I'm looking at the two-dimensional effective description, at linear order, that's it. Right. That is here. Okay. Yes. Okay. See, all I'm doing here is I'm taking, this is the parameter that you were talking about, right? I'm just leveling both of them by epsilon, and then I'm keeping terms here to order epsilon and here to order epsilon square. So terms that will involve 2 delta G will not have any phi. One delta G and one phi will come. Yes. No, the field redefinition that one does is only to get rid of the derivative terms involving phi. One does a field redefinition. I don't know if we are talking. The derivative terms can so that is why this action is just like this, phi square r, some potential of phi that does not involve derivative. So and that's what is okay. And then when you do this, then you do this, then you get phi. This is capital phi. This is small phi, and r. But this is r for background, so r0 plus 2 by L square. All I'm trying to say is that at linear order, and this statement is not really specific to what I am doing. If I am writing an action around the background, then to linear order, I can only have boundary terms. Which two? These two. Just 4D.
So that must be also a solution to those.
Exactly. Yes. 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 This result is just from 4D. No, not entropy. No, metric. I'm just writing the near horizon, near extremal geometry. The near horizon, near extremal geometry is not ADS2. This part is ADS2. I mean, ADS2 cross S2, I mean 4D. But this part is corrected like this. And this, you look at this. This is a minus sign here. This is different. I mean, this is a solution that just few days back Samir also talked about. Sorry. So this is the horizon radius, and this is T. So when this T is the temperature of my system. What eta? Huh? Sorry. This eta? Yeah. Okay. Yeah. Okay. Good. Yeah, eta equal to 0 is my horizon. No, these are like right. Some value. So that is what I should be interested in, right? My region is R minus, I mean, my near horizon region would be R minus RH. In this case, your RH is at eta equal to 0, is very, very less than RH, but still it is non-zero. In fact, in terms of eta, so just for this, just for this, eta equal to 0 is my horizon. So for in presence of this, it will be corrected. Eta of order 1, yes. Yes. Yeah, some eta max, right? That's what we take, and then finally we take that 20. Yeah. Say again, please. T. Yeah, that one can think of. Yes. Yeah, T, yeah, I'm okay to take T small. I want to basically work in T small. Okay. And then you are saying that we can actually forget about this part.
That's the linear order in T, but that's also the order in T. The Schwarzian normalization.
Yeah. Mm-hmm. Right. Yeah, I have to check that.
Once the radiation of the sphere radius gets frozen, then these start to become
very
sphere radius Asymptotically, it's varying, right?
Mm-hmm.
Once it stops varying, that close to substantially close to the horizon.
Mm-hmm. Yes.
Then the effect of that IISER exists isolated required. So it's a variation of the sphere as a function of radius, which is responsible for deviation from radius, right?
Oh. But see, what we can see here is the sphere radius is being corrected by this function, right? Because this gamma ij, I should have written this is just the sphere. Yeah, in large eta it's growing, exactly.
For an theta order 1, basically, yeah, you can say at the theta order 1, the correction is small in the sense that as well as t is small, the correction is under.
But this, yeah, this whole non-triviality is also because of this term, right? It is.
Are these are the same order, right?
Yeah.
So these variations are become important at the same value of theta.
Yes, I would think so. Yeah.
Theta order 1, that's where this comes out. That was the jetty function. Below that,
only below that I can ignore this part. And one can just take this and try to find the other part of it. Okay, possible. I'll try that out also. So yeah, that's all that I had to say. Thank you.
Are there more questions? If no, then let's thank Nabamita for this nice talk.
Thank you.
Thank you.
Hey, I am here actually till weekend. Monday I'm not here. I mean, I have to go to Chennai. So all the Monday I'm leaving Bangalore on Tuesday, but for whole Monday no, I came on last Saturday. I didn't see you either. Yeah. I thought you were not coming to the department.
No, I came a couple of times, but I didn't see you.
Yeah, probably I was just sitting inside.
Yeah.